Good morning. It is November 9th, 11 o'clock Eastern. Whatever time zone you're in, good morning, good evening, good night. Um, I want to welcome you to Liburdi Engineering's LinkedIn Live event. We do these technology discussions from time to time. Um, so these are intended to be discussions, and we'd appreciate if you've got any questions or comments to put them in the comment box, and we'll try to address them at the end of our session. And if we don't do that, we may be able to email you or call you with more details. I want to now introduce our speaker for today. We have Robin Reese with us today. Robin graduated in 2018 from McMaster University with a bachelor's in materials science and engineering. She's worked at Liburdi for 5 years now and has experience in gas turbine condition assessment, metallurgical life and failure analysis, and she's a key process engineer responsible for our LSR coating production and developments. She has responsibility for the implementation of new slurry coating binding agents, robotic coating spray, and production quality control. I promised that I wouldn't say anything about the fact that she's a wonderful baker as well and has been known to bring in some of the best cookies to the office. So Robin, we're very interested to hear what you have to say about turbine coatings today. So welcome.
Thanks, Doug. Today I'm going to be talking about aluminide coatings, their functions within a turbine engine, the benefits in part life optimization, and specifically focusing on Liburdi's aluminide process, LSR, which stands for Liburdi Slurry Repair. So at its highest component, a standard turbine engine consists of two sections. The cold section, which consists of the intake and compression areas, and the hot section that covers the combustion and the exhaust. These different sections present different requirements concerning the stresses, temperatures, and environments the parts are subjected to. These requirements can then be answered by a variety of different materials for the parts themselves, which are then supplemented by the addition of various coatings. So coated components behave as a composite system, the substrate or base material providing the desired mechanical properties against the stresses of the engine, while the coating provides the required surface behavior to combat the environments they're running in. Coatings are employed in the cold section of the turbine for corrosion, erosion, wear resistance, and in the hot section with the elevated temperatures, coatings are used for oxidation and hot corrosion resistance, wear resistance, and temperature reduction. As a member of Liburdi Turbine Services within the Liburdi group of companies, our main focus is mainly on the repairs and issues of the components within the hot section at the elevated temperatures. So one of the major issues we come across in the hot section is oxidation. Oxidation is the chemical reaction between metal and oxygen at high temperatures. This reaction consumes the metallic elements and forms a scale. Over time, the scale can reach a point where it can act as a protective barrier. However, that does require the scale stays in place. When we introduce the cyclic nature of the engine with its startups and shutdowns, we induce stresses that can cause spallation of the scale, leaving the base metallic elements once again open for oxidation and consumption. The pins shown on the slide are a variety of materials commonly used in turbine engines, showing us how much of a range of oxidation resistance exists. The very poor Rene 80 on the left has a tendency to form poor oxide scales that spall quite easily, allowing for higher degradation over time. Meanwhile, on the far right, the Merle 72 has the excellent oxidation resistance, but doesn't have the mechanical properties required for the needed stresses of the engine. So hot corrosion is accelerated oxidation caused by the inclusions of salts and sulfides in the engine. Hot corrosion can come in two different types. Type 1 is high temperature hot corrosion, occurs roughly in the range of 850 to 950 Celsius, while type 2 is low temperature hot corrosion, occurs in the 650 to 700 Celsius range. The salts and other contaminants depositing on the surface at these high temperatures lead to accelerated attack and material loss. These contaminants can come from a variety of sources, such as external salts in the air, often seen in maritime environments, or from the fuels used in the combustion section. You can see on the LM2500 row 2 vein on the right that it has experienced some heavy hot corrosion attack and material loss, and this can create inefficiencies within the engine. To protect against oxidation and hot corrosion damage, an aluminide diffusion coating is applied. What the aluminide coating does is offer up a reservoir of aluminum, which is more easily oxidized than other metallic elements within the base alloy, to form a protective, stable oxide layer with good adhesion. To form this coating, a diffusion reaction occurs between an aluminum source and the superalloy substrate it's being applied to. The interdiffusion that occurs during this reaction can create several kinds of layers within the coating itself, consisting of the outermost area, which is rich in beta nickel aluminide on nickel superalloys, transitioning into compositions that include a mix of elements from the originally applied aluminum source and pulled from the superalloy base. And finally, a solid solution diffusion zone that separates coating from the base material. These aluminide diffusion coatings can also be applied to cobalt-based superalloys as well as the more typical nickel-based. In these cases, though, there is less of a transition from outer coating to diffusion zone, as only the beta cobalt aluminide is formed. This process can come with its own difficulties, as this coating tends to be a bit more brittle and can affect the thicknesses that can be achieved. Here at Liburdi, it is one of our commonly offered repair services. Additionally, aluminide coatings can be applied to iron-based alloys, though it is much less common. So these coatings are an inward diffusion process, which, as previously stated, means that some of the base material's elements and phases are incorporated into the microstructure of the coating. These incorporated elements then become integral in the overall performance of the aluminide coating. You can see in the micrographs shown the visual representation of what the diagram on slide 6 was showing, with the diffusion zone 4 on the right-hand micro being separating the coating and the substrate, and the way the phases are distributed as you move outward from the substrate towards the beta aluminide-rich surface. Being an inward diffusion reaction does mean that some of the base material is consumed when the coating is applied, but much less than the consumption and damage that would be caused without it. Depending on the required coating thickness and the dimensional requirements of the part, this can limit the number of times a coating can be removed and reapplied during repair. One common method of applying the aluminide coating is pack cementation. So pack cementation is an activated aluminide process where the parts are exposed to an aluminum salt mixture called the pack. The pack is then heated, producing a gas phase that will react with the parts to deposit the aluminide coating. Depending on the process, the parts can either be above or in contact with the pack. Some of the disadvantages to this process are the need for large waste disposal, which is of often toxic material. The process itself has to be at a high temperature, meaning that there is a high capital cost associated with it. And because the reaction takes place wherever the gaseous pack comes in contact with the parts can be very difficult to mask. An alternative to the pack cementation that we use here at Liburdi is the slurry coating method. Slurry coating is done by combining a powdered aluminum alloy with a binder and applying it to the surface of the part. Application of the slurry is typically done by atomized spray. This can be done robotically for consistency or manually for parts that are more specialized and unique. Applications, once the slurry has been applied, the parts are put through a diffusion heat treatment that will drive off the organic binder and cause the aluminum alloy to melt and react with the base alloy to form the aluminide layer. These heat treatments are often harmonized with rejuvenations or other required heat treatment repairs. When you compare slurry coating to the pack cementation, we can see some of the advantages of the slurry. As the slurry application is a room temperature process and the heat treatments can be combined with other repair steps, there's a lower cost associated with it. The different components of the slurry are either driven off in the diffusion process or create the coating, meaning that a lower amount of waste is created and lowering our environmental impact. Some of our LSR processes can also be done using a water-based binder, lowering the environmental impact even further. The slurry itself is very customizable, as variations in the alloy compositions can be included as part of the alloy powder to tailor the coating properties to what we need. Also, because we separate the deposition from the diffusion steps, it can give us a higher amount of quality control, as it allows us to perform checks before the actual diffusion, such as thickness. And finally, the parts themselves are much easier to mask during this deposition. Being easier to mask means that our masking efforts are much more customizable. We can apply coat and no coat areas to the level of precision up to being able to spell words legibly onto a part surface, including our own company name, though this is much less tended to be included in our standard repairs. This also allows us to apply multiple coatings on some parts, such as the 24G vein shown on the left. This part requires the oxidation and hot corrosion resistance on the airfoils provided by the aluminide coating, while the shrouds need the temperature protection of a TBC coating. With the LSR slurry process, we can set up these two different coating methods in a streamlined way to not interfere with one another and to get the best optimization of the part. Additionally, that separation of deposition from diffusion allows us to go back and clean off areas that are difficult or near impossible to mask before or during the deposition, once again allowing us a higher level of precision. Overall, it can allow us to take on more specialized jobs as required. For example, recently we had a set in-house that had a small area around a platform that experienced rub damage. We were able to take those parts, recoat the area without the need for a full repair and without affecting the rest of the part. A common addition to the aluminide coating is platinum. It's often incorporated into aluminide diffusion coatings to improve cyclic oxidation resistance and is often used in components that see a lot of potential hot corrosion damage, such as that LM2500 Row 2 vein as shown before. The platinum dissolves into either a solid solution in the beta aluminide or forms a mixture of platinum aluminide phase with the beta aluminide. So the micro on the left shows the LSR platinum aluminide coating with the light region showing the platinum rich layer of coating. Another typical variation of the aluminide coating is the chromium silicon aluminide, or the Kralsey coat. The added in chromium increases the hot corrosion resistance, while the silicon adds both hot corrosion and cyclic oxidation resistance. Overall, both of these additions lower the critical amount of aluminum needed for proper protection. The other advantage to this coating, it is overall lighter, which means when we apply it, there is minimal weight addition to the blades, which can help with our engine efficiencies. A wide variety of elemental components can be added or substituted to tailor the properties of the coating to these desired effects. While our main additions of platinum, silicon, and chromium are widely used, we are continuously working on developments and continuous improvements to better answer the needs of customers as engine designs and requirements change. One of the helpful things for our process and for our continued developments and improvements is the ability to see our own coating returned to us after service. For example, we first implemented the water-based LSR on parts in 2016, and since then have consistently gotten back the same parts at their next repair cycle and been able to see how they fare under service. This particular blade, the LM1600 LPT, we coated in our water-based LSR back in June of 2016, and the same set returned to us in May of 2022, having undergone approximately 40,000 hours of operation. We were able to see from our analysis that the coating was fully intact, plenty of beta aluminide still remained on there, and no large damages had occurred. Being able to get this active feedback helps us with our process of continuously being able to monitor and improve our LSR slurry. Thank you so much for listening to my presentation. I'll answer any questions best I can.
Question is how much aluminum is in the LSR coating after diffusion? thinking that superalloy has typically what, 5% or something in that ballpark?
Typically in our LSR coating, we end up with a 25 to 35 weight percent, I believe.
Okay, so significantly more than the base superalloy.
Yes.
All right. So I guess that's the basis of the protection, is the higher aluminum content.
Yeah, the addition of it does allow the aluminide, provides a lot of aluminide to be consumed should any of the protective scale fall off.
Okay. Um, Another metallurgy type question. Superalloy has many elements. Which ones are good for the coating? Because I guess you mentioned they were inward made. And which elements are good for the coating? And are there any elements in the superalloy that are bad for the coating?
I believe it takes chromium and silicon are often components within the base alloy that get pulled into it. I believe, go back to, we also see a lot of molybdenum, titanium, and cobalt can get pulled into those interstitials as well. That often help out with that. For detrimental ones, I'm not as familiar with.
Okay, so conceivably some might be
There's always
not
the
as good.
potential.
So that I guess I guess there could be a substrate effect, a subtle substrate effect.
Yeah, though it should also be dwarfed fairly largely by the amount of aluminum content in the coating.
True, yes. Okay, and here's a process type question. Are there any size limits to what can be coated? For example, can you coat combustion parts?
I believe we have coated combustion parts. Typically, we can't do it robotically. They do have to be manually sprayed. But beyond our ability to put them through the furnace, through the diffusion cycle, we can deposit the slurry on any size of part.
Okay. So the limit isn't the application of the coating. The limit is fitting it into the diffusion furnace.
Yes.
Okay. All right. Well, that makes sense. Okay, folks, if there's any more questions, if you put them in the comments box, then they will pop up. Okay, here's one come in. Is aluminide diffusion coating used on first stage frame 9 buckets? We know the first stage bucket is coated with TBC and overlaid with M. Crawley. So I guess the question is a frame 9 stage 1 bucket, which is normally M. Crawley plus TBC. I guess it would be in that order. So is diffusion aluminide coating an option for a frame 9 bucket?
I'm not as familiar with parts specific, to be entirely honest.
Well,
I would need to look into what specifically it would be used. Because the coatings that are applied to it are typically used for a specific reason for it. Having an M. Crawley or a TBC provides a different sort of protection or requirement correction that the aluminide might not present. And without the full knowledge of what that part on my end is doing, I don't know if I'd recommend one or the other.
Okay, but you raise a good point there. There are different coatings for different purposes. And an M. Crawley plus TBC is typically used for thermal control. And a diffused aluminide is typically used for oxidation / corrosion control. It doesn't lower the temperature of the base metal.
Correct.
So you're kind of got an application there where you need thermal control, and an aluminide isn't really a good thermal control coating. I think that's a good takeaway, right?
Yeah.
Now, having said that, there are aluminides inside the frame 9 stage 1 bucket. It's coated internally. So can you tell us a little bit about LSR, and can you coat internal passages?
We have done internal passages for larger industrial parts, including certain buckets. I'm not sure of the specific one. The slurry does allow us to apply it in a different method. It doesn't get aerated the same as an external part, but it can get applied into the part itself and drained out to apply a layer of aluminide coating.
Okay, so you can coat internals using the slurry process, which,
Depending on the size of the internals, yes.
okay, all right. So that would be valuable to the repair cycle.
Mhm.
Okay. Another question has come in. What does the silicon do to help corrosion prevention in the coatings?
The silicon, you can kind of see it on the thermodynamic chart on the slide that I have up. The silicon also provides a fairly stable oxide to help that protective scale. It's one of the reasons it's very commonly used alongside the aluminum as part of the coating.
Okay. Another question has come in. Is chrome-free something Liburdi is offering or considering? Do you see a demand for this? And by the way, great presentation. So, do you have a chrome-free aluminide, and do you see increasing demand for chrome-free products?
Um, do you mean in the addition of chromium into the actual powder? Because most of our typical LSR slurries are made with the aluminum and silicon. The chromium is an addition that we use on more specialized parts.
Okay, so the base product or the most common product is chrome-free by definition. You don't
Yeah.
have chrome in. And are you? And I guess the question is, are we? And I can only assume we're looking at health and safety issues and hexavalent chrome. Does your process use hexavalent chrome or does it use metallic chrome?
It uses metallic chrome.
Okay, so you don't get into a hexavalent health and safety problem at all when putting this coating on? Okay, so to answer that question, the chromium isn't a problem in this type of a process. So that's good to know. Okay. Yes, and there's a clarification here that we were talking hexavalent chrome 6 problems. It's a non-problem in this particular instance, luckily. Very good. Any other questions, people? If you want to type quickly, we have a few more minutes and we can take a few more questions. Meanwhile, Robin, what's your favorite kind of cookie?
This time of year, ginger snaps.
Wonderful, wonderful. I'm always going to go to chocolate chip, but that's me. We'll give people just a minute to type a little faster. Maybe while we're waiting, Robin, this process, how long has Liburdi been using this LSR process?
Oh, geez, I don't. It's been long since before I came in. um,
So I think safe to say more than a decade. So you've got lots of experience under your belt, so to speak, with this
yeah,
process and with this product.
considering our water-based came into play around 2016, and we had been coating it with a different type of oil-based binder before that, we can definitely say we've been doing it for a while.
So it dates back a couple of decades. Okay, good. So there's lots of proof in there. Another question has come in. What does the inspection process look like after the return of a repaired part? So if a part comes back in from service, how do you inspect the coating? And so how is that done?
So it's kind of two parts. We have our non-destructive types inspection processes to see if there's any oxidation damage or anything where that the coating has been consumed and you can see oxidation of the part itself. We also tend to take blades for a destructive life analysis reasons. And in those cases, we're able to take several sections through different blades or veins as required and to analyze the performance of it from there under microscopic observation.
So of a set of 50 or 100 blades, you sacrifice one so that the others can be diagnosed and live again.
Correct.
Okay, very good. Any other questions out there, folks? Okay, I don't see anything else coming in. Let me just check here. Okay. One question is, are the coatings REACH compliant? REACH. And I'm
Yes,
afraid I
they
do
are.
not know what that acronym means.
Yes, they are all REACH compliant.
Okay. That's an environmental requirement?
Yeah.
Okay. So there you go. We do have REACH compliance, folks. Okay. Well, I want to thank everybody for attending our LinkedIn Live event here. I think we're getting a little bit better at it as we do it. So thank you so much, Robin Reese, for joining us and giving us an overview of LSR and a little bit on how it's inspected and produced. I want to thank everybody for tuning in. If you have any follow-on questions, comments, concerns, please do put them into our LinkedIn feed or contact Robin, and we'll try to get an answer for you. And if we don't have an answer, we'll make something up. All right. Thank you again, folks. Appreciate you attending. Have a great day.